going here. Let's do, what is that number? Number three. Number three. I will zoom in here. Does everybody have it? I have an extra copy if you don't. Everybody has theirs, their book. Anybody else need it? Number three. Gives the density of these two balls. The balls are released, they accelerate upward to the surface. What is the relationship between their accelerations? I'll go and start your clicker. When you know the answer, go ahead and click in. All right, just a few more seconds. All right, I'll stop at 33. 33. Okay, awesome. A is right. Here, remember the buoyant force, FB, is equal to the density of the fluid times the volume of the object times the acceleration due to gravity. So since each of these have equal volume and they're both held in a container of water, they're both going to have the same buoyant force. So if I were to draw the free body diagram, I would have the buoyant force, which would be equal for both of them, and then the only other force is the weight. And so the net force, if they're going up, presumably that buoyant force is bigger. It's going to be FB minus FW. So the one with the smaller weight will be the one that accelerates up at a greater rate, because then the net force will be bigger if FW is smaller. And ball A has the smaller density, so it's going to have the greater acceleration. It'll have the smaller mass, the smaller weight, and the greater net force. Let's see if there's another one here. I don't think there was. Oh yeah, let's try number 2. Anchor made of iron weighs 833 newtons. It's now suspended in seawater. What is the tension in the chain? If it were just hanging in air, it would be 833 newtons. What is it now that it's suspended in seawater? Look, guys, on a problem like this, you could probably look at the answers and probably be able to pick one right away that is going to be the correct answer. So just try that, see what you think. All right, let me ask you a question. When the anchor is submerged in seawater, is it going to appear to have less or more weight? Less, right? It's the apparent weight. Remember that lab with the little cylinders we submerged in water? They feel lighter. They have an apparent weight that's less than the actual weight. So I know that C and D cannot be the right answers, because C has equal to the weight, but I know that it has to be less than that. And D has greater than the weight, so I know that can't be it either. So go ahead and put in your answer. I'll stop at 140. All right, good. B is the right answer here. You get rid of C, you get rid of D, and then you're left with only A and B. But gosh, A just seems really small to me, so I would have felt really comfortable just picking B. But if you just want to check that, then I'm looking for the apparent weight, I'm going to call it AW, That's equal to the actual weight minus the buoyant force, which is 833. That's given, minus the, remember our buoyant force is rho Vg. That's the density of the water, which is 1025 kilograms per cubic meter. The volume of the object. Now this is a little tricky because I have the density and I have the weight, so I have to figure out what is the volume. And so the volume is equal to, what is it, mass over density? Is that right? Is that right? Rho is, yeah, that's right. It's the mass over the density. The mass is actually equal to 883 kilograms divided by the density of iron, which is 7,800 kilograms per cubic meter. And so if I look at that, say I'm looking at 80 over 8,000, I can approximate that as 80 over 8,000. Get rid of that, so it's 1 over 100. So I'm looking at 1 over 100 for my volume times G, which is 10. So I have 833 minus 100, which gets me pretty darn close to that answer. So what I did here, you're going to have to be sort of quick with the numbers and making these sort of estimations. But I found the volume, because I'm looking for the apparent weight, the actual weight minus the buoyant force. The actual weight is this. Buoyant force is the density times the volume times G. But up here I define the volume, but fortunately the numbers sort of work out easily to get me a volume equal to 1 over 100. I just approximate this at 1,000. 1,000 divided by 100 is 10, times 10 is 100, so I get 833 minus 100, which tells me that this can only be the right answer. That's really the only one that's close. As you practice more and more, you'll be able to pick out the right answers. You'll just be able to look at them like you should just been able to look at that and say, well, gosh, B has to be the right answer. Okay, let's look at we're going to skip over the molecular forces, but really they just talk about two things, cohesion and adhesion. Cohesion is when materials stick to one another, and adhesion is when a fluid sticks to the side of its containers. Let me write that down. Cohesion, when the molecules of a liquid stick to one another. You've ever done this thing where you take a cup of water and you fill it up to the very top and then you start dropping pennies into it? You ever done that? Oh, you should really do it. It's cool because as you drop more and more pennies into this, your water just really bulges out over the top. And if you're very careful, if you don't break that surface tension, which is due to the cohesion between the molecules of water, you can get a really big bulge on top of the water. But you have to start with a really full cup of water and then just drop pennies into it very slowly. Don't try it next time you're out, I don't know, wherever it is that you go out. Like just get a glass of water, but that's the all the way to the top, no ice or anything, because that will break the surface tension. And drop pennies in it very slowly, being careful not to break the surface tension. That's due to the cohesion. And then adhesion is when molecules stick to the surface. Just not to one another, but to some surface. And this is the result of a meniscus. So when we do a meniscus like this, I'm sure y'all seen this in chemistry lab, it's because the molecules actually stick, to the side. Okay, let's look at flow. There were a couple things that came up with flow. Viscosity, laminar turbulent flow, and the Poiseuille equation. I go down from here? All right, so fluid flows. Just some words first. The viscosity. This is described by the variable eta, Greek letter eta, It describes how thick it is or how sticky a substance is. It's actually a measure of the frictional forces between the molecules of a material. So, you know, viscosity. Which is more viscous, water or maple syrup? Maple syrup, right? It's stickier, it's thicker, it has a greater viscosity. So we use that to describe fluid flow. It would be very important for fluid flow. Also laminar and turbulent flow, or rather laminar versus turbulent flow. Almost always when we're talking about fluid flow, we'll be talking about laminar flow. Turbulent flow is very difficult to describe mathematically, and there's a lot of modeling that has to happen to describe turbulent flow. Turbulent flow, by the way, you know the love dub sound I'm talking about? When you're listening to your heart, you get the love dub, love dub, love dub. That's due to in your heart when it brings blood into one of the chambers. I forget which one it is. It might be all four, but when it brings blood into one of those chambers, you get this really turbulent flow because the fluid's going so fast, the blood is going so fast, it just goes turbulent. And turbulent often makes the sound, the love dub sound. Love dub, love dub. All right, so laminar versus turbulent. Laminar just means that it's all sort of straight like this, and turbulent means that as it flows, you're going to get a lot of turbulence. All right. The Poiseuille law, or the Poiseuille equation, Poiseuille's equation describes fluid flow, Q. This is the rate of flow. It's equal to pi r to the fourth delta P divided by 8 eta L. So this is how quickly something flows or fluid flows in your system. Like for example in the circulatory system. R is the radius of your vessel, blood vessel, whatever. Delta P, this is your pressure differential. This is your viscosity. This is the length of the system. Let me write that down. R is the radius of the vessel. Delta P is the pressure differential. Anytime you have a viscous fluid, you need a difference in pressure in order for that fluid to flow. If you have any type of viscosity in your fluid, you're going to need a pressure differential. That is where you have to have high pressure on one side, low pressure on the other side. And we have that with our circulatory system, right? We have the heart creates a high pressure, it pushes it through the body, and then it comes back. When the blood comes back to your, the vena cava, when it comes back to your heart, it has a very, very low pressure because it's lost all of its energy basically as it goes through the circulatory system. So that's the pressure differential. Eta is the viscosity. And L is just the length. All right. These are called streamlines. We used these last year, sort of. Streamlines just show, we use these to describe fluid flow. You can imagine that if you have a particle in the fluid that it stays along the streamline. All right, let's look at the continuity equation and Bernoulli's equation. The equation of continuity. The equation of continuity says that the rate of fluid flow is always constant. All right, and it looks like this. It says that A1, that's the area, times V1, that's the speed, is equal to A2 times V2. So for example, if I have a pipe that looks like this, I have a big area down here, I'll call this A1, I have a certain speed, V1, have a smaller area down here. That's A2. Is the speed here going to be bigger or smaller than V1? Bigger or smaller? It'll be quite a bit bigger, right? The velocity here, the speed of the fluid will be bigger. You ever put your finger on the end of a garden hose? Like when you put your finger on the end of a garden hose, it causes the area to decrease, which increases the speed. Okay, so here the speed is bigger. So what this means basically is that this is always constant. If the area goes down, the speed goes up. And it's just like putting your finger on the end of a garden hose. This happens too, by the way, in your circulatory system as well. Or does it? Right? I mean, we start with our artery. Right? Artery is pretty big. Stick my thumb in it basically. And then it splits up into those arterioles. And then they further split up into, I don't forget what they're called. But anyway, eventually you get to capillaries. Are capillaries bigger or smaller than the artery? Or the aorta? They're smaller, right? They're a lot smaller. But does blood flow more slowly or more quickly in your capillaries? Is it more slowly or more quickly in the capillaries? It flows very slow in the capillaries, actually. The blood flow goes very slowly. So how do we describe that with the equation of continuity? How does that jive with the equation of continuity? That's what it's like our system, right? What are your classes?
Nope.
Okay, so the aorta is really big, right? And it is true that capillaries are a lot smaller, but there are a bunch of capillaries. So if you add up all their cross-sectional areas, their area is actually quite a bit larger than the aorta. So the continuity equation still holds with the circulatory system, even though the area of your individual capillaries is a lot smaller, the overall area is a lot bigger. Okay, lots of good fluid flow stuff in the circulatory system. Okay, now Bernoulli's equation. This describes the conservation of energy. It's actually the conservation of energy density. That is, that the total amount of energy per unit volume remains the same. Conservation of energy density, all right, because it's really a measure of energy per unit volume. And it says that the pressure plus rho GH plus 1/2 rho V squared, that this is equal to a constant value. Some of this should look like energy to you just a little bit. Like for example here, this should remind you a lot of mgh, which is gravitational potential energy. But look, if I just put an m over v, then it becomes rho gh. Then it's gravitational potential energy per unit volume. And this should remind you a lot of 1/2 mv squared. But if I put a little v in there, it now becomes energy per unit volume, or 1/2 rho v squared, because m over v is rho. And then pressure, it's a little more, you have to think about it, work as force times displacement. But if I divide this, it's a little more complicated, but it's work per unit volume, okay? This comes about from the conservation of energy. The big thing with Bernoulli's equation that'll come up in applications, and we'll see problems later, and your book talks about this, is that when the speed goes up, the pressure goes down, right? So if you speed up a fluid, the pressure will decrease. And that seems sort of counterintuitive, because if you think about putting your finger on the end of your water hose, we've already said the speed of the water does what? Increases or decreases? It increases because you're decreasing the area. A goes down, V goes up. So if that water increases in speed, Bernoulli's equation says that it will decrease in pressure. And that doesn't really seem like it's true, right? It seems like it's hitting you harder when it comes out, right? But it's not really. There's a lot less of the water, and so the pressure that it's imparting on your body is a lot less. Okay? So the takeaway with Bernoulli's equation, I don't know if you ever have to actually calculate anything with it, though, you know, you might. But the big takeaway is that if V goes up, P goes down. And this is the idea behind an aircraft wing. This is a wing. I have my air that goes over it, my streamlines here. Here, because it has to travel a long distance over the curved part of your wing, we have a high speed fluid, and down here we have a low speed fluid. When I have a high speed, that means I have a low pressure, which means I'm going to get a lift, low pressure on top, high pressure on bottom. All right. Right, so that's Bernoulli's equation. Again, I doubt you're going to have to make any calculations, but that whole thing with the Venturi, which we'll look at here in just a second. In your book on page 131, they describe a Venturi. Lots of health applications for this too, like when you have entrainment systems. Have you ever seen an entrainment system where, thank you, you know what I'm talking about, an entrainment? Shoot, what it's called. When you have lung treatments or whatever, and you want to get fluid into your lungs, they'll use this Venturi system where you have like a tube and they blow a high-speed fluid across it, and in the tube you have your liquid. The high-speed air across the top of it causes a low pressure, which means these little particles of liquid will come up and be entrained into that stream of fluid. You know what I'm talking about? You ever seen one of these? No? Okay. Well, let's look at the Venturi. Again, this is on page 131. And we had very similar questions in 101 last semester. You have these standpipes to represent our pressures. And remember, if I have a big area here, I have a small velocity, that means I'm going to have a big velocity over here. And if I have a big velocity, that means I have a low pressure, which is represented by these standpipes right here. The height of the standpipe gives the pressure. The height of the standpipe is proportional to the pressure of the fluid. Remember in the class last semester, we talked about how at a point below a certain height of fluid, that pressure at that point is equal to rho times G times H. That's where that comes from. If I have a larger column of fluid over that point, then I'm going to have more pressure. That also has to do with when we measure our... I'm sorry, you have to go. Okay. What was I saying? Oh, when we measure our blood pressure, you get that little column of mercury. That's a similar thing. The height of the column of mercury measures the pressure. Now let's do a couple of questions. Let's try this number 5. This is going back to what we did before with Pascal's principle. Let's try it. Megan, do you have your book? So try that number 5. It has more to do with Pascal's principle. Number 5 there. All right, just a few more seconds. still missing one person. I'll stop. There we go. All right, let's see. Hydraulic lever. When the same bed as patient with the work card is doubled, how can the cross-sectional? The answer here is A. Let's see. So I want to have this hydraulic lever. It's going to lift or perform a certain amount of work, W. I want to double that work. If I double the work, that means that I want to double the force. So here, imagine this is my hydraulic lift, thank you. I'm putting in a certain force here. I'll call that F1 over A1. I want to know what can I do to this platform over here, what can I do to A2 in order to make my force twice? Because I want to double my work. Remember, work is equal to force times displacement. If I double my work, that means I double my force. In order to double my force, I have to double the area. Right? So the answer there is, what do we say? It's A is the right answer. Let's try another one. Let's try number 12 here. This has to do with Bernoulli's equation. All right, I'll stop at 45. 45. And B is the right answer. This is a lot like what I was saying earlier, that if I have this curved wing, the speed of the airflow is bigger on the top. So since I have a high speed, I have a low pressure. And that provides lift for your wing. When do we get out here? 6:15, is that right? Okay, we're almost done. We'll wrap up soon. Let's try number 8 here. I think quasi equation, if you want to look back at your notes. All right, I'll stop at 1 minute. 1 minute. Okay, looks like we're split between A and C. I can see how you might think A is the answer, but C is the right answer. You think A is the right answer, and it would be right, because you got these two cross-sectional areas, right? You have A1 and A2, and so you think, well, gosh, I should be able to use the continuity equation, but I don't know what V1 is. So since I don't know what V1 is, then A isn't sufficient information. In fact, a lot of these could be correct. Here, B, the Reynolds number, that has to do with turbulence, so we're not really worried about that. We're not going to deal with that. That's not really enough to give us the speed. C is the right answer, and it goes back to that Poiseuille equation where Q is your rate of fluid flow. It's actually a volume per unit time, meters cubed per second. But from that, you can get the, the linear speed of the fluid, and that was that pi r to the fourth. What was it? Pi r to the fourth delta p. A to L. Yeah. So you have all those things. That's your delta P, that's your eta, that's your L, this is our R to the fourth. And then also this Q is equal to volume per unit time. So that's the same as area times distance over time. And this would be our linear speed. And since we know the radius, then we also know the areas. Okay? Let's see. A couple more things. We'll be out of here. Circulatory system, let's say they actually talk about this whole thing with the capillaries in your book, but just like we already said, that you do have this constant blood flow throughout your body, and the reason that it slows down in your capillaries is because your overall area gets bigger. The other place where fluid flow comes into play is when we breathe, and it goes back to something you might have learned in chemistry called Boyle's law. PV is equal to a constant. I don't know if you remember from chemistry, but Boyle's law was put together with Charles's law to create the ideal gas law, PV equals nRT. But this is really all that we need to think about how we breathe. Y'all think it'd be right? Now, your lungs are not muscles. Right? Your lungs are just sort of, I don't know, bags or whatever that sit inside your chest. So in order for you to breathe, it's your muscles that are inside your chest, not your lungs that will expand or decrease in size. So when you breathe, you make your chest cavity bigger, and what that does inside your chest cavity, if I make volume big, what does that do to the pressure? If this has to be constant, if my volume increases, what happens to the pressure? It decreases, right? So if I make my chest cavity really big, volume decreases, and that causes all that high pressure air that's outside my mouth to rush into my lungs. Because I have a high pressure outside, low pressure inside. And then when I exhale, my chest cavity decreases in size, so V gets small, P goes up, I have high pressure inside, low pressure outside. That's Boyle's law. And it explains how we're able to breathe just with the muscles in our diaphragm. And that's it for that chapter. Let's see if there are any other good questions. I think we hit most of the good ones. Yeah, I think so. I think we'll wrap it up. But I just want to, gosh, man, y'all look really terrible when y'all come in. I know this is not a very fun class. Like, there's a lot of material, and it's just sort of drudgery, but it will help you. I mean, the physical science portion of the MCAT can be difficult, but this will help. Every little bit that you do will help on the MCAT. So, just keep trudging along and doing what you're doing. It's good because your MCAT, for many of you, is still pretty far out. Summer or maybe the following summer for you, so it's good that you're preparing now, but keep your heads up, okay? Try not to look so sad all the time.
Is the fluid stuff that you just taught today going to be included on Mallory's test? Or
No, it'll be on the next test. So we have one more test, and the fluid stuff will be on that, and then also we'll do this here and stuff like that. Okay? I'll send y'all an email out letting you know when we get closer to that. But on Friday, you'll be stuff on organics, so make sure you bring your organics book on Friday.
Our circuit test for the I don't think it's
It hasn't been what?
the grades haven't posted.
Okay, I'll get a hookup away tomorrow and take care of it, okay? Y'all don't have any sessions. I mean, do sweat them a little bit, because if you sweat them, you'll get more out of them. We just want to see that you're taking them a little bit seriously, okay? Okay, I'll see you. I'll see many of you Wednesday.